started in just a minute here. All right. So welcome to lecture 4 of Comp 551. Today we're going to talk about linear classification. Can you guys hear me all good at the back? Yeah, cool. Okay. But before we get into the lecture content, the one important major announcement is that Mini Project 1 is out. So the project specifications are available at the link there. You can also get them on My Courses. It'll be a group project, so you'll make groups on My Courses. This group feature on My Courses, I'm still working out all of the kinks with. So maybe, for now, get started on the project, form your groups. The exact submission on My Courses should work, but I want to do some more beta testing with the TAs. And so what is this project going to be? Calling this Machine Learning 101. So this is a project where we're really going to be putting into practice the things that you learned in the first few lectures. So you'll only need material up until last lecture for this project. So this is based on real data. I went and extracted some data from the website Reddit for people who know Reddit, and what you're going to try to do is predict the popularity of comments in this data set. And a quick disclaimer here that this is real-world data that I scraped from a community called Ask Reddit. It's a question-answering community on Reddit. And so not only is it messy in the sense that there's all kinds of statistical weirdness, it's not going to satisfy all the really pretty assumptions that you might assume often is the case because it's the real world. Data is messy, but the other thing also is that there may well be offensive content and other things hidden within this data set. So just a heads up, I do give you raw text features, and this is just things that people are saying on the internet. So I don't recommend you read through all 12,000 comments because that's probably a waste of time anyways, but just a heads up there. So what you're going to do in this project, you're going to extract some features, some very simple kind of feature information from this data. You're going to make a train, test, and validation split from this data. You're going to implement linear regression. So we're going to ask you implement the closed form solution. So this is basically one line of linear algebra, which you're going to do in Python and then using the NumPy framework. So we give you, explicit instructions for what sorts of frameworks you should use. You should use Python. You should use NumPy, but you aren't allowed to use an out-of-the-box linear regression solver. You have to code it yourself. So you're going to do the closed form solution. You're going to implement gradient descent. And you're going to compare a bunch of different model settings. We ask you to come up with some new features yourself that improve the model performance. And so this first project or mini project is kind of the least open-ended. As the course goes on, things are going to get more and more open-ended, but we still are going to ask you to submit a write-up. We give you the freedom to kind of, if you want to go further and do more exploration with the data or try out different kinds of features. Maybe you want to, plot how the speed or the convergence time for the gradient descent changes as a function of the learning rate. You're welcome to have a bit of flexibility there. We give you minimum requirements that you need to satisfy. And I think the thing to have in your mind is that if you just satisfy the exact minimum requirements kind of perfectly to the T, that's like a B plus-ish type thing to do, maybe an A minus, right, if you don't have any mistakes. If you want to really push it and get, a full 100%, you need to do a little bit of kind of creativity, go a little bit beyond just the bare minimum requirements. But we provide suggestions on reasonable ways to do so. So again, maybe you add in a nice figure. Maybe you do some investigation about how the convergence of gradient descent depends on the learning rate or depends on different learning rate schedules. Just something beyond the bare minimum requirements is necessary to get a perfect score, but you can do very well in this course if you just perfectly meet all the bare minimum requirements. So it's a little bit up to you there of how far you want to take it. And as I've mentioned many times, this is all completed in groups of 3. The groups, you submit these things together on My Courses, and everybody in the group gets the same grade. So an important thing, this assignment's due in 2 weeks, so if you don't have a group yet, this is the time to find one. You can use the discussion board on my courses to look for group members. There's 2 weeks to do this. It's not an excessive amount of work, but again, depending on your background level, if you've never programmed in Python, if the tutorial last week or this week, there's one again tonight, was your first experience with Python, this might take a bit of work. So that's the thing, is this is, how long this project takes depends a little bit on how much, you're having to ramp up on, Python and NumPy and, refreshing your statistics. So, it's up to you. It's leave the time, look at the spec, it's up there, make plan with your teams. 2 weeks is more than enough time, given that there's 3 of you. So that's the summary, and I know you'll have lots of questions, so I will make another discussion forum on my courses, just particular for Mini Project 1 issues, and we'll have that up today at some point. The other quick update is these self-assessment practice quizzes. So the first thing I want to say is that there have been a few technical hiccups. As you all know, this is my first, or maybe you don't, but this is my first time using my courses because I'm a new professor at McGill, and it's different from the system that I used previously at the other institutions. I think we've worked out most of the kinks in the system, and that was part of the reason why this week also didn't count for grades. So if there's any issues that you think are still, happening, be sure to post something on the discussion board, because we are going to do a final round of debugging over the weekend to make sure that when you have the quizzes next week that count towards your grade, they actually work completely as they should. To give you a quick sense of what was happening here, so roughly last I checked, this was last night, there was over 250 people who completed it, so that's awesome. There's roughly a 75% average, which is, I think, pretty much where I expected things to be. A couple of these questions were tricky. They were tricky in the sense of, especially some of the probability ones that, maybe you're just like kind of got tripped up by the wording or something. So I think you should be getting 4 out of 5. I think especially if you got less than 4 out of 5 on quiz in the attempt 1, I'd recommend trying attempt 2 now knowing what to expect. But you really should be getting at least 4 out of 5 right. Otherwise, the course is going to be pretty difficult. Again, maybe you want to, just try and make up for the fact that you don't have as much probability background, but it'll be rough. So that's to give you a sense. Overall, things went pretty well, but try it again if you got less than 4 out of 5. Are there any questions? Yes. Great question. So yeah, are the quizzes based on the previous week material? Yes. Always based on the previous week's material. So this first one is based on previous, as in prerequisite material you should know. Yeah, the quizzes will always be, in some sense, there to kind of keep you up to date with the course. The quizzes this week were maybe involved a bit more kind of mathematical calculations than the average quiz. In future weeks, they'll occasionally just involve kind of trivia, like fact questions based on the lectures, just to make sure that you're, again, keeping up with the material. Any other questions on the project or quizzes? Yep. It is not 100% overlap. I believe there are, yeah. In future weeks, it'll be almost 0 overlap. For this week, it's not 100% overlap. So not all the questions are identical. But there is, and this will be the same every week. There'll always be 5 questions, and there'll always be, if there's a question on the theme of, say, learning rates next week, there will be a question on learning rates in attempt 1 and attempt 2. There'll always be kind of parallel questions in both attempts, but they won't always be identical. Generally, they won't be identical. Yes, so this is one of the technical hiccups. Always questions and answers and explanations will be available after the quiz deadline. And ideally, the system should be showing you what questions you got wrong right after you submit. This doesn't seem to be working properly for everybody right now. But yes, you will get to see all the answers. This will be very useful review material for the midterm, for example. So that'll all be available after the deadline, all the answers and explanations. Yep. Is the project, that project link should work now. It's not working? Okay, let me, is there a typo there? Oh, yes, fix it on the fly. I just uploaded this just before class, so I just was missing a files there. Let's. Oh. Yes, there it is. Sorry, there was a typo. I fixed it. It'll be up in the corrected slides right after. Thank you for pointing that out. The link on my courses is definitely correct, though. It's been tested. Okay. That's enough of that for now, unless there's any final questions. Yes? Oh, for the quizzes? Yeah, let me see. Yes, I will try to do that. It'll take a bit of wrangling with my courses, so it might not happen right away, but I'll try to get that done for you. Okay, so now getting into the actual content. So just to recap what we talked about last week, obviously we talked about linear regression, but probably the most important thing, and again, what you're going to have to do in the project, is you're going to have to learn to partition your data into a training set, into a validation set, into a test set. And why do we do this? It's because what we care about is how well our model performs on data it's never seen before. So we need to simulate this by training our model on one part of the data, validating it on a part of the data we've never seen before to kind of try out different models, etc. And then finally, at the very end, we report our number to the public, say, using this held-out test set. And this is really important, again, because generalization is our goal. We want models that don't just perfectly fit the things we show them. We want models that can perform well in new scenarios they've never seen before. So in previous lectures, we talked about supervised learning. We talked about the difference between classification and regression. Bit of a broken slide there, that's okay. So previously we were talking about linear regression, so where the goal is that we want to take some input features and we want to make a prediction about some numeric target. So say the change in size for a tumor. Today, we're moving on to the next most important kind of machine learning, which is supervised classification. So classification problems, very similar to regression. We're given a data set. We have a bunch of input features, X. We have our targets, Y. But now our target variables, they are discrete. So what this means is that they're going to be either binary, which is a 0-1 variable, or a true-false, or they can take on a categorical set of values, and this is called multi-class classification. Going to focus on binary classification for the most part in the next couple lectures, but we'll talk about how to generalize these things to the multi-class setting without too much difficulty. So what are some actual real-world applications of classification? I would say that classification is probably the most popular variety of machine learning. I think when a lot of people think about machine learning, really the first sorts of tasks that come to mind are classification tasks. So there's text classification, so maybe spam filtering in emails. A big one is sentiment analysis. So in sentiment analysis, the idea is that you want to take some text and predict whether or not this text conveys a positive or negative attitude. So maybe if you're a company, you care about the attitude that people are expressing towards you on Twitter, might affect your stock price. Image classification, I talked about this in the first lecture. This is a really big active area of machine learning. There's entire conferences dedicated to this. So maybe you want to do face detection, detect different objects. You want to have a recognition system for pedestrians in a self-driving car. We talked a lot about this example of predicting cancer reoccurrence as kind of a simple example we're talking about throughout these lectures, and even recommender systems. So where what we want to do is recommend, say, a news article to a user or recommend a movie to a user. These are, in fact, a variant of a classification problem. There, the number of possible classes is really huge. So if we're recommending movies, there's hundreds of thousands of movies we could recommend, but in one sense, it's just a really big multi-class classification problem. So I'm going to start off with a really simple example of classification, returning again to our running example of trying to predict whether or not a particular tumor, its cancer, is going to reoccur. So here we're going to keep things simple. We're going to assume that we have a single input feature, which is the nucleus size. So this is how big, in some sense, the tumor is. And then our binary output. So we have a 0 for no recurrence and a 1 for recurrence. And what I've shown here at the bottom of the slide is histograms plotting this nucleus size, our feature, for these two different classes. So you can see that for the no recurrence class, it looks like the nucleus sizes are generally a little bit smaller. The distribution is a little bit different here. So it's the histogram where on the y-axis we have the number of examples that fall into this bin, and then the nucleus size on the x-axis. And then on the right, this is the same histogram for cases where we see recurrence. So we can see there's definitely a signal here, right? So if you're looking at this, it's obvious that, well, if we wanted to predict no recurrence, we're probably going to base that on the tumor having a smaller nucleus size. So how might we do this? Well, the first thing you might think is, well, we have 0, 1, it's a numeric value. We learned linear regression, so why don't we just run our linear regression algorithm using this 0, 1 output as our y variable and see how we do. And then, of course, this is going to give us a numeric prediction, but we can just threshold or maybe want to interpret the output of our model as a probability. This is kind of the first simple thing. You're basically saying, like, why don't I just run linear regression with a 0, 1 y? It doesn't break the model, or it shouldn't. Now, it doesn't break the model, but this performs terribly. So what I'm showing on the right is actually the linear best fit if you were to do this. So again, on the y-axis, this is the nucleus size, and then the x-axis is our prediction for y. So again, really y is a 0, 1. It only takes 0 or 1, so that's why all the true data points are at the top or the bottom. But our linear regression model doesn't know that. It's just making predictions as if this is a continuous variable. And you can see that, well, this thing doesn't really seem to be fitting anything. Like maybe there's a tiny bit of signal there, but just taking a linear regression model and using that to try to make classifications where you actually have a discrete output, it's not the best idea. So, of course, we're actually going to come up with a better model. It's still going to be a linear model, but we're actually going to think about what is the right way to approach the classification task where we're actually taking into account the fact that we have a discrete output variable. So, backing up a little bit, there's really two high-level views of binary classification. And these are not kind of opposing or competing views. These are just two different ways to look at things, and they're pretty complementary. So in one view, we have the probabilistic view. So here, our goal is to try to estimate what's the conditional probability that our output y is 1 given our input features. So we're trying to get this conditional distribution. What is p of y given x? So what is the likelihood that this variable is 1 given the input data that we know? This is going to be the focus. We're going to talk about some other techniques, but the probabilistic interpretation is the one we're going to start with. The other interpretation that's going to become more prevalent a little bit later on in the course when we start talking about decision trees and support vector machines is the idea of decision boundaries. So in a decision boundary, our goal is, instead we just want to think about how can we partition the input space so that we can classify points according to what region they fall in. So basically, in our example of this recurrence, you might say, where can we draw a line where we say, if the nucleus size is greater than 18, then there's recurrence, else there's no recurrence. And here, we don't need to have some probabilistic interpretation. We're just saying, look, we've drawn a line, and when things fall on one side, it's no recurrence. When they fall on the other side, it's recurrence. Now, focusing now on the probabilistic view, within probabilistic models of classification, there's again another split. And this split is between what is called discriminative learning and generative learning. And this is a very important distinction. There's many machine learning paper written about kind of comparing discriminative versus generative models. So what is the difference between these two? In discriminative learning, we're doing in some sense what you'd expect. We're just trying to directly estimate what is the probability, the conditional probability that y equals 1 given our input features. So we're directly trying to estimate p of y given x. In generative learning, we're flipping things on their head a little bit and going about this prediction in a bit of an indirect way. And how do we do that? Well, what we do is we actually are going to first get an estimate of what is the probability of the features given the target. So instead of p of y given x, we're doing p of x given y. And then we're also going to get an estimate of just what is the marginal probability of y. So just how likely are we to see true or false. And using these two estimated values, we can then actually just apply Bayes' rule and flip these things around to get an estimate of p of y given x. So here with Bayes' rule, we're getting p that y equals 1 given x. This is going to be equal to p that x, probability of these features, given that y equals 1, times the probability that y equals 1 and then over p of x. We don't need to worry as much about this p of x term, but what's important is that we're getting these two estimates up here. And why might we want to do this? There's a variety of reasons for using generative models that we'll go into more and more in following lectures. But the basic intuition here is that this can sometimes be a little bit easier, and you can also kind of use more external information. So for example, maybe you have a lot of information about p of y, and then you can leverage that to make your predictions even better. So this generative learning approach is kind of unfolding things a bit with Bayes' rule to give us a bit more flexibility. And these models generally can perform well when you have smaller amounts of data. But for today, again, narrowing in once more, we went from looking at probabilistic versus decision boundaries, and now within probabilistic, we have discriminative versus generative. We're narrowing in, and for the time being, we're going to focus on the basic discriminative learning approach. So we're trying to just directly estimate the probability of y given x. And now we come to a bit of math. So we're going to take this probabilistic view of discriminative learning, and what we want to do is we're going to suppose we have two different classes, so simple binary classification, and what we care about is the probability of a given input, a given data point, having the class y. Now, what we're going to do is first take this p of y equals 1 given x. This is what we want to estimate. We're going to use a little bit of probability identities to rearrange this as follows. So we've taken this conditional probability. Now this is equal to the joint divided by the marginal. Then we're going to take this joint that we have here, and we're going to flip that around and say this is the conditional probability that of x given that y equals 1 times probability that y equals 1. So this is just applying Bayes' rule. And then on the bottom here, we're going to unpack this probability of x. So how likely is our input features is going to be how likely are these input features given that y equals 1 times the marginal likelihood, and then given that y equals 0. So it's a bit of a mouthful, it's a bit of math here, but this is just Bayes' rule. After applying Bayes' rule, we're going to do some algebraic rearranging, and then some more rearranging. I'm not going to painstakingly go through all of this. And then at the very end, what's important is that we've rearranged things into the somewhat scary looking expression here, where our original, what's the probability of y given x, we've fiddled around with Bayes' rule and some transformations into this 1 over 1 plus the exponent of the natural logarithm of this thing here. And why have we done all this? It's because we end up with this simpler form where we say the probability that y equals 1 given x is actually going to be equal to 1 over 1 plus the exponent of negative a, where a is this particular equation shown down here. So let's back up and unpack that a little bit and explain why this makes sense. So first off, we computed this a function. So this a function shown down here. Now this a function, this is a function that tells us what's called the log odds. So this tells us how much more likely is this data point to be a 1 compared to this data point being a 0, right? It's pretty simple, actually, once we've simplified it a lot, is that we're just saying what's the ratio of this y output being 1 divided by this y output being 0. And then we're taking the natural logarithm. So this just tells us, it's called the log odds, the very fundamental quantity. It just tells us how much more likely is this thing to be a 1 than to be a 0. The other important component we have here is what we call the logistic function, which is often denoted with a sigma, which is a bit confusing because sigma is also used to denote variance, but we'll just have to deal with that. So the logistic function is 1 over 1 plus the exponent of this a, negative of this a. And what this logistic function looks like if you plot it is it looks like what I've shown here in the bottom part of the slide. It's this nice function where if we go all the way to negative infinity, this thing equals 0. If we go all the way to positive infinity, this thing equals 1, and it has this nice kind of S-shaped transition as we go past 0. So what you can think of this logistic function as doing is you feed in a real value that can be anywhere from negative infinity to infinity, and it squashes this real value into a probability. So this takes as input the entire number line and squashes that to between 0 and 1 in a nice smooth way. It's a really important function, really useful because it allows us to transform any input that is a real number into a probability. And in this case, this score that we're feeding it, which tells us kind of, how likely is this thing to be a 1, this score is just the log odds. Now, you might wonder, well, why did we do all that? We had, Bayes' rule. We didn't need to introduce this log odds idea and this logistic function. Well, that's because in practice, we don't actually know what the log odds is. If we knew p of y equals 1 given x, then we'd be done. If we knew what the conditional likelihood is, then we wouldn't need to use machine learning to solve this problem. So the reason why we did this is because the approach we're going to take is we're going to approximate or model the log odds with a linear function. So in reality, in the ideal world, our log odds a is equal to this true underlying value. We don't know this value, but we're going to approximate it with a simple linear function. Any questions at this point? Cool. So yes, the important thing here is that we've done a bunch of rearranging so that now we've taken the original challenge of estimating how much more likely is y equals 1 compared to y equals 0, and we've turned that into a linear estimation problem. And another way of looking at this is that now what we've done is we've said, let's feed into this logistic function, again, this function which takes real numbers and maps them to probabilities. Let's feed into this logistic function the output of a linear regression model. So this is how we're solving the problem, getting back to the beginning of the lecture when we said, well, how can we just use linear regression to make classifications? Well, we can't just directly apply linear regression, but we can apply linear regression after we've kind of squashed it through a logistic function. And if we're going to think about the decision boundary kind of variation of this, the decision boundary is a set of points for which this A equals 0. So we're set of points for which this linear equation equals 0. That's our separating boundary. So again, here we have both a probabilistic interpretation as well as an interpretation in terms of a decision boundary. Okay. And down here, just reiterating the main equation, and for terminology, this is always called logistic regression, is the term you will see if you want to Google or Wikipedia to get further insight on this. That's the term to use. Okay, so now we've figured out how we can make a binary prediction or predict a probability in a sane way using a linear model by squashing it through this logistic function. But now the challenge is, how do we actually learn the weights of this model? Unfortunately, it's not as easy as just running linear regression and then slapping a logistic function on top. You have to be a bit more sophisticated. So at this point, it's worth recalling or noting kind of what this logistic function means in this setting. So in particular, what we have is that if we take the logistic function, so it's the sigma here, applied to the output of our linear model, this gives us the probability that y equals 1. 1 minus this gives us the probability that y equals 0. And now, given this information, a very useful thing we might want to compute is the likelihood of our data. So what we care about is how likely is the set of variables, the set of output targets y, given the feature information we have and the weights we've learned. So when we were talking about linear regression, our kind of approach was to say, well, we care about this squared loss. In here, we care about our likelihood. We want to know how good are we doing at predicting these targets. Ideally, if we have a perfect model, then we have a likelihood of 1. This means that our model is kind of perfectly assigning a probability of 1 to everything that actually happened and 0 to everything else. So this is this likelihood term here. What does the likelihood term actually unpack into? Well, it's a probability, and these are a set of independent events. So getting back to our assumptions about independence and being identically distributed, we're assuming that all these y's are independent. So if we want to get the probability of our entire data set, this is the product of the probability, the likelihood for each independent data point. So we're taking this product over our n data points here. And this equation may look a little scary, but what this equation is just a fancy way of writing that if the data point is actually a 1, so the real answer is a 1, the likelihood, the probability we give that is the logistic function. If it's 0, then it's 1 minus our output. So we're using the exponents here just to do this in a fancy way, because these exponents are always just 0 and 1. So it's going to knock out one of these terms every time. Okay. Yep. Yes. So here so the question is, here the subscript means the data point. Yes. Here the subscript means the data point. This is something where I apologize for being fast and loose, but it's annoying and difficult to do it really any other way, where generally you use subscripts to denote data points as well as feature indices. Generally, I'll use I when I'm talking about data points and J when I'm talking about feature indices. But it's almost always evident from context. But this is just a notational issue where subscripts sometimes denote data points, sometimes they note they denote a particular entry in a vector or a matrix. Any other questions? Yeah. Yes, so just going over the likelihood function. So the part in the red box or the part in the green box? The green box. Okay, yes. So what this likelihood function is it's what is the probability of our data set, so our target variables, given our features in the model we've learned. So this is saying that, so you can think in the simplest case, suppose your data was just, you're trying to model for some reason just one binary variable, one data point, then your likelihood would be you have some fancy model for predicting that, and say this one value is a 0, and you give that thing a probability of 0.2 of being 0, then your model has a likelihood of 0.2. So it's basically just saying what is the probability that the model you learned, what is the probability it assigns to the true target values? It's a bit of a, takes a little bit to wrap your head around, but it's a really fundamental function, because what our goal is when we're trying to optimize a logistic regression model and actually many other machine learning models is we're trying to maximize the likelihood. So the idea here is that, again, in a perfect world, we would assign a probability of 1 to the true data. We would say that, look, I have this set of email spam, a bunch of things that are spam and aren't spam. I'm giving a probability to each of these ones, and if my model was perfect, I would give every spam a probability of 1 of being spam, and every no spam a probability of 0. So my likelihood would be perfect, because whenever it was spam, I would have a 1 here. This would be 1. Whenever it was no spam, this would be 1, because I'm predicting 0, and so this whole product would end up being 1. So the best you can do for likelihood is 1. The worst you can do is 0, if every time you predict exactly the wrong answer. Does that clarify? Okay. Yeah, so as a heads up, there's a little bit more math in this lecture compared to previous ones. Okay, cool. So our goal is to maximize this likelihood function. We want it so that when we run our model, it assigns a high probability to every true positive and a low probability to every true negative. Again, if it was spam, we want to give 1s to all the spam, 0s to all the non-spams. But there's one challenge here about directly optimizing this likelihood function, which is that taking the product of a bunch of small numbers is really hard to deal with on a computer. There's other reasons why this is a problematic thing to work with, but really if you think about having 10 million data points, and every one of these individual values here is something between 0 and 1, we're going to taking some number that's between 0 and 1, basically to the power of 10 million. And that's going to run you out of even your machine precision on your laptop. So it's not reasonable to actually work directly with this raw likelihood. But there's a pretty easy solution to get around this. Yeah? So why you can use, yes, so why in the first place can we use this multiplication? So I think the easiest way to think about this is that we have n independent data points, right? So if we want to say what's the likelihood of our entire data set, these are independent events. So this is the likelihood of seeing all of these things. The joint is the product of all of them. So that's why we're taking a product, is because we're trying to say what is the joint probability of our entire data set. And then why this particular form here with these sigmas and y's, that is because this part here is actually just equal to this shown here in the bottom part of the slide. So this is saying that if the true yi is equal to 1, then we're just saying what is the probability we predict for this thing being true. If the true yi is equal to 0, we have 1 minus this, which is our probability that we give for this thing being 0. So the interpretation here is that we're taking the product. For every data point, we're saying, what is the probability that I give for the right answer? And then doing that for all our data points and multiplying all these probabilities. Does that clarify a little bit? Okay. Yes, and feel free to slow me down and ask lots of questions. This is fundamental stuff, and this lecture is a little heavy on math, and it's fine if we don't get through everything today. We can pack some stuff into next Tuesday. Okay. So again, we're taking products because we're trying to approximate this joint down here. So we compute that by taking the product of a bunch of independent probabilities. But the issue is that this function here that's no longer showing up is hard to optimize because it can be really small. So we do a really simple thing, is we just take logarithms. So unfortunately, I can go back here, we've taken this function here and we've just taken the natural logarithm of it. And if we remember our log identities, when we have the log or the ln of something that has an exponent, then the exponent moves down here. And so at the end of the day, what we end up with is what we call the log likelihood. And it has this form down here. It's just the logarithm of this likelihood equation I showed before. I won't go into painstaking detail for how this is computed, but this is a really, really fundamental and important equation. This is the log likelihood for logistic regression. And I'm going to try to restart this. Aha. So we have this log likelihood that we're trying to estimate. And in fact, what we've ended up after all these derivations from this likelihood idea is we've ended up with a function that sometimes is called the cross entropy. And so, in fact, one way of looking at it is that we're trying to maximize the likelihood of our model. But in fact, this is also equivalent to minimizing a particular loss function, which is called the cross entropy loss. So we derived this log likelihood. We want to maximize this function. This is the likelihood of the data given our model. But we can also think about minimizing the negative of that function. And people call that the cross entropy loss. So oftentimes there's this kind of relationship equivalence between thinking about maximizing the likelihood of a model versus minimizing some loss. And you might say, well, like, where is this cross entropy thing? How would anyone ever come up with such a loss function? We won't go into details on it, but in fact, there's a nice formal information theory interpretation of this cross entropy loss. And the basic idea is that it measures how many bits of information we need to correct the errors made by our model. One second. I'm just going to see if I can switch to HDMI. Unfortunately, if I switch to HDMI, then people can't see slides on the recording. So just 1 second. Okay, I think we're coming back to life here. Hopefully. Okay, we're back to life. Hopefully we don't get more technical issues. I will maybe buy another adapter just to be safe for next class. Okay, so coming now to a bit more of a high-level concept after all of that math. So there are probabilistic interpretations of many different loss functions. So here we talked about how can we learn the parameters of our logistic regression model by maximizing the likelihood. We transformed that to the log likelihood. And at the very end, I said we came up with this thing that's also known as the cross-entropy loss. Now, this is actually a very common thing. So in some machine learning courses, instead of the first lecture on linear regression talking about minimizing a squared error loss, they might actually present it as maximizing the likelihood of a linear regression model. And so all the time there's going to be this kind of duality between this maximizing likelihood view or this minimizing loss view. And for the sake of time today, I am not going to go through the exact derivation of how we can interpret linear regression as a probabilistic model. The basic way this works is that we have to assume that our true data is some linear function along with some Gaussian independent noise, again, where this independence assumption keeps coming up. And then we can represent the likelihood with a Gaussian function. We can take logarithms. And at the end of the day, we end up actually with a loss function that is the same as a squared loss, because these terms are constant. This is material that maybe we'll come back to the end of the lecture if we have time. Otherwise, highly recommend that you review it offline. It's not critical material for understanding the course, but I think it's good for your kind of spiritual growth in machine learning. Okay, so we talked about likelihoods and losses, and again, under certain assumptions. I think this under certain assumptions is underlined because this is where all of these independence and all these assumptions on the structure of our data come in, is that if we want to kind of make an equivalence between a loss function and a likelihood, we need to make assumptions on our data, like these IID assumptions. And another thing worth mentioning here is that not all losses are created equal. So we can come up with all kinds of losses. So we talked about a squared error loss when we were doing linear regression. For classification, or for linear regression, we could instead use an absolute error. We could use a 0-1 loss for classification. So instead of this cross-entropy thing, we could just say, did we get it right or did we get it wrong? But these loss functions are often really hard to optimize, for one, and there's no way to interpret these losses in terms of a nice probabilistic model, or no straightforward way. So why do we use the losses that we use? So why do we use the squared error loss for linear regression? Why do we use this cross-entropy loss for logistic regression? It's because they're theoretically grounded, and with that theoretical grounding comes guarantees for optimization and a lot of other nice properties. So you can just kind of go crazy and come up with weird loss functions and find ways to take their derivatives and optimize them, but there's a reason why we use the loss functions we do, and that's ease of optimization and theoretical grounding. And one other quick point that I want to just kind of highlight right now is that losses are not the same as error metrics. So this cross-entropy loss is this way we can optimize logistic regression, the way we can do linear classification, but if I told you, hey, look, my model has a cross-entropy loss of 0.02, you'd be like, okay, sure. So obviously we can use these things to train our models, but if we want to actually interpret our model's performance, then we want to use more interpretable error metrics. So in particular, for linear classification, we probably want to train using cross-entropy. This is the most standard thing to do, and cross-entropy is used to train not just this logistic regression model today, but used to train the best deep learning models that are coming out this week. But after we've trained this model, if we actually want to know how well our model's doing, we're going to report something like the accuracy, so the percent of the time we make the right prediction. Now, that's a hard thing to optimize, again, because it's not really a differentiable nice function, but if we want to tell somebody how well we're doing, we're not going to say that my model has a cross-entropy loss of 0.2. We're going to say I have an 80% accuracy. And we're going to have a whole lecture on evaluation functions, or half a lecture on evaluation functions in lecture 6. Okay, so back to logistic regression, bit of an aside there. So what we're trying to do, again, is we're trying to learn this linear model, learn these parameters W, so that we can maximize this likelihood. and we turn this likelihood into this log likelihood because that's a bit easier numerically to deal with. So what we want to do is we want to maximize this function or minimize the cross entropy loss, which is just the negative of this function. And so how are we going to do that? How are we actually going to find the W parameters, the weights for our linear model that give us the maximum value for this function? Well, the same way we did it for linear regression. We're going to use calculus, take derivatives, and that allows us to find the optimum of this function. In this case, closed form isn't quite as nice and easy to come up with as in linear regression. So instead, what we're going to quickly derive, or not so quickly, is the gradient descent rule for logistic regression. So again, what we want to do is we want to maximize the likelihood of the model. Likelihood is monotonic with log likelihood. Taking a logarithm doesn't change the maximum of a function. So we want to maximize this thing. We're going to do that by taking the derivative with respect to our weight parameters and then taking steps, shifting our parameters in the directions that we're told by these derivatives, that we get from these derivatives. Okay, another somewhat heavy slide. So what we're trying to do is maximize this likelihood, or equivalently minimizing this cross entropy loss, shown here, often denoted CE. So this cross entropy loss is a sum over all of our data points. We have a y times the log of the logistic output plus 1 minus y times the log of the inverse of the logistic output. So what we're trying to get to do gradient descent is we need to know the derivative of this loss function with respect to our weight matrices. We have to know this derivative because it tells us where to push our parameters to optimize this function. So the first thing we're going to do is just get the derivative of this part on the side here, this first term. And we're going to walk through this because it's useful knowledge, and it's also going to bring up a couple useful derivative identities for logistic regression that are kind of for the sigmoid or the logistic function that are very useful to know, and things that might be on exams, stuff like that. So first thing we're doing is taking the derivative of this log of the logistic output. So the first derivative rule we apply, what all of us should know, is that the derivative of the log of something is going to be 1 over the input to the log. So that's where we get this term here, just the basic derivative of a logarithm equation. Next, we get this term here. This is where we're taking the derivative of this full function, but we have to take, by the chain rule, the derivative inside here. And conveniently, this logistic function, which is this 1 over 1 plus e to the power of something, this weird function, actually has a really nice derivative. So when you take the derivative of the logistic function with respect to the weights, it's just equal to the logistic function times 1 minus the logistic function. Quite nice. So this saved us a lot of pain. And this is something to definitely remember. You get a cheat sheet on the exam, probably something you should write down on that cheat sheet. And then finally, we have the most straightforward part of the taking the derivative here, which is just taking the derivative of yt times x with respect to w, or wt times x, sorry, with respect to w is just x. Now, we can do all this again for this side, applying similar rules. Another useful rule to know is that the derivative of 1 minus the logistic is 1 minus the logistic, and then the logistic and with the negative input. So, somewhat useful thing to know. We have taken this whole messy thing using these derivative identities, useful to remember. And now we have rearranged these things in a nice way. And unfortunately, my slides are breaking again. And the important thing to know here is that at the very end of the day, I apologize for these slides breaking at the last minute, is that after we've done some rearranging of this big messy derivative term, it actually ends up being quite simple. What we get is just the sum over all of our data points, x times y minus the logistic output, So this is our derivative. If we're running gradient descent, we're taking, to get our updated weights, these are going to be our old weights plus our learning rate times our derivative, or the negative of our derivative. Now, this is the gradient descent for logistic regression. I will clean up if this is an issue with the slides being saved funny. I'll fix that. If it's just the current weirdness with the projector, I'll look into that too. But this is the full model. Now we can derive the gradient for our logistic regression model. That allows us to optimize our logistic regression model, and everything is happy. Now, one thing I wanted to say on that slide, but I'll move off of that mess for a second, is how we do this optimization. So in your mini project and in this slide, we're doing this really simple thing where we're saying we want to optimize a function. We want to find where it's maximized or minimized if it's a loss. So we're just finding the gradient or the derivative and taking steps in that right direction that's pointed to us by the gradient. And we're applying a simple learning rate. And maybe we have some schedule for choosing this learning rate. Now that is the kind of basic approach that works quite well. There's also a lot of other more sophisticated approaches that use this gradient signal and can actually improve how fast your model converges. We're not going to go into detail in those things. In this course, we'll talk about a little bit once we get to deep learning. But it's just important things to know, like if someone says, like, oh, you're using plain gradient descent, why aren't you using momentum? Or why aren't you using a second order method? So these are techniques you can use to speed up the process of kind of walking down the loss function to the minimum. Okay, any questions at this point? Yep. To keeping the log terms as in, oh, to taking the log. So is there any? Yes. So actually something that's an interesting thing to do if you're very curious and have lots of time is try to, first off, derive the gradient descent update rule without taking the logs. It's not quite as pretty. Not that that was pretty, but it's actually just, some of these identities are a bit easier with logarithms, so that's one. The other issue is numerical stability. So like I said, if you derive the gradient update rule for just the plain likelihood optimization, run gradient descent, it's going to be pretty hard to make that work if you have more than 1,000 data points, because these numbers are going to be tiny, these likelihood numbers. And so it's going to be really difficult. You're going to have to use a huge learning rate, and things are going to go really weird. But all of that said, in a perfect world, if you had perfect machine precision, and you ran gradient descent on likelihood and gradient descent on log likelihood, for logistic regression, those are going to come to the exact same answer. Again, applying the log didn't make our model better, it just made our optimization easier. It's a very good question. Any other questions? Okay, cool. So just to give a quick bit of recap, so talked about the two different probabilistic approaches to binary classification at the very beginning, and today we focused on discriminative learning. So we're trying to directly estimate the probability of y given x. And this is this logistic approach. This is what we focused on. Now we have the gradient descent for this. We can optimize this. And then the other type of binary classification is this generative learning approach. So here we're trying to separately model the p of x given y and p of y, and then using Bayes' rule to take these two values and actually get our prediction. And in the next lecture, we're going to talk about the kind of classic generative approach, which is called naive Bayes, which is kind of a funny name, in my opinion. And then we're going to show why that might be a reasonable thing to do and what benefits that might have compared to logistic regression. So just giving a quick recap, and I apologize again for the messiness and the breaking of the slides with the projector. Like I said, I will get cleaned up things posted, and I will also buy a new adapter in case that is the issue that is causing that. But just to give a quick recap of what you should take away from today. So you should take away the basic definition of the linear classification problem. So again, we're talking about classification. This is linear classification. We're not just applying linear regression to classification because that does not work. What we did was we derived the logistic regression approach. And if we can remember, if my slides agree with me at all, that all the magic had to do with the use of this logistic function, which has this really nice property that when you feed any big, small, whatever number into it, it outputs a nice probability. And sadly, this is going to take too long with how slow this projector moves, so we're going to give up. The other thing you should take away from today is this high-level conceptual point about the difference between maximizing a likelihood and minimizing a loss. So in our first few lectures, we were talking about minimizing a loss, and now today we talked to this other interpretation about maximizing likelihood. So like I said, I had some slides that actually derived the maximum likelihood loss for linear regression. We do have a few minutes left, but I won't take you through that because it's a lot more math. But like I said, do go through these slides where I derive the probabilistic interpretation of linear regression. These are useful things to know. This is something where conceptually you should be aware of, say, for exams. And another key point is that even though we use sometimes weird-looking loss functions like cross-entropy, when we want to actually know how well our model is performing, we use sensible error metrics like accuracy. So there's a difference between the loss that we use to optimize a model and the error metric that we use to talk about our model. So some final notes is that there is a second Python tutorial tonight, 6 to 8 p.m. in Automas. The material is posted on the course schedule. So if you didn't attend the first tutorial and you're on the fence, you're thinking, should I maybe attend tutorial 2? You can go and look at that material and see whether or not it's totally basic. NumPy will be covered in a basic sense. And please do get started on Mini Project 1. It's going to involve Python and NumPy. I'll hang out up here for our next few minutes if people have more questions.